Hi guys, we're going to talk about constraint optimization today. But first let's look at unconstrained optimization. So the classic problem is minimize f, and let's take a simple case of f equal to x squared. It's pretty obvious to see that this function is always greater than 0 because it's the square of this variable x, and so the smallest value it can take is at x equal to 0 and then f equal to 0. So we already know that this is the point that minimizes this function, and it's easy to see that when we plot it. We plot x here and f here, and the minimum point is the origin. The f is 0, x is 0, and I'm sure we all know that the reason that the origin minimizes this function is that the tangent here is parallel to the x-axis. In other words, the derivative of the function is 0, and that doesn't hold for any other point. At no other point along this curve is the tangent parallel to the x-axis. You can see that it starts off pointing in the negative, towards the negative y direction, points less and less that way, finally becomes 0, and then starts pointing upwards. So we know that in order to minimize a function, we want the derivative of that function to be 0, and if you extend this to multiple dimensions, let's now call f x squared plus y squared. You can pretty much carry this logic over, and here you can see again that x squared and y squared both have to be greater than or equal to 0, so their sum has to be greater than or equal to 0 as well. So again, x is 0 and y is 0 minimize this function, and if we plot it on this three-dimensional axis, x is along the x-axis, y is along the y-axis, and we'll say f is along the z-axis, then you'll get a paraboloid. And when you go to multiple dimensions, the concept of the derivative is replaced by the gradient operator, which is simply the derivative with respect to x along the x direction and the derivative with respect to y along the y direction. And when we apply this operator to f, we get 2x along the x direction and 2y along the y direction. So it's interesting to note that this is just 2 times x and y, which means that if you go to any point on this paraboloid and you want to find the gradient, all you need to do is draw the vector from the origin to this point, which will be x comma y by definition, scale it by 2, and you will get the gradient. Okay, so now let's get to the interesting part, which is constraint optimization. So let's stick to this objective function we've been working with faithfully, but now let's make things a little interesting by adding a constraint. So we still want to minimize f, and we add a constraint cxy equals x minus 5, and we require this to be 0. So now what will this constraint look like in the same plane? Let's actually draw it here. We already have a paraboloid, and if we draw this constraint as well, we'll go to x equal to 5, and it will basically be a plane parallel to the yz plane, and it will intersect our paraboloid in a curve. And it's actually not that hard to work out the equation of this curve. We have z equal to y, x squared plus y squared, and x equal to 5. This implies z equal to 25 plus y squared. which is a parabola in the YZ plane, and it's easy to see that this guy is minimized when y square equal to 0, because it can't go any lower than 0, and at that point the value of z is 25. Let's visualize this three-dimensional curve with a plotting software. I'm going to use matplotlib with Python, and for those interested, I'll include the code in the description. So we can see that in gray we have the paraboloid x square plus y square. In green we have the plane x equal to 5, and the light green portion is the parabola of intersection. Let's take this back to a place where we can draw on it, which I've already done here. And you can see that with this green parabola, this is the minimum point, which happens to be z equal to 25, x obviously equals 5 because that's our constraint, and y equals 0 from here. In order to minimize z, y has to be 0, because if it's any larger than that, it can only add to z. Because it's a square, it can't really it can't take anything away from it. Now we want to come up with a generalized framework for constraint optimization. So obviously there's going to be derivatives involved, there's going to be gradients. In the unconstrained case, we knew that the answer was simply the origin, and at that point the gradient of f, which is 2 times x and y, was simply 0. Now how do we extend this to the constraint case? First of all, we know, as I mentioned before, that the gradients for this particular f simply point outward if from the vector joining them to the origin, right? So if we take point 1 to the left here and point 2 to the right here, then the gradients of f, del f1 and del f2 at points 1 and 2 simply point along the vectors themselves. And now let's consider the gradient of the constraint. Cx equals x minus 5, and del c by del x will equal 1, and del c by del y will equal 0. This implies the gradient of c is always 1, 0. So it will always point along the x-axis. So if we draw that here, we'll get it. We'll see something like this. So this is del c1, this is del c2, and now let's look at the minimum point as well, which is point 3. At point 3, you have del c1 pointing, del c3, excuse me, pointing along the z direction. And what about del f? We see that del f also happens to point along the z direction, along the, x direction. And maybe that's the property that makes this point the optimum of the constraint problem. And that happens to be true, and the reason for that is very intuitive. As long as you have the gradient of the constraint not equal to the gradient of the objective function, you can move along a direction So let's say over here we choose to move along the parabola, and by doing so we are perpendicular to the derivative to the gradient of c, which means that we are not changing c. However, we are not perpendicular to the gradient of f. So let's call these directions that are going along the parabola at points 1 and 2, d1 and d2. We have del f1 dot d1 is actually less than 0 because I hope you can see the angle between them is more than 90 degrees. Del f2 dot d2 is also less than 0. However, del f1 times, del c1 times d1 equals 0, and del c2 times d2 also equals 0. So this means that at these points, if we go along d1 and d2, we are not violating the constraint, yet we are decreasing the objective function, which is exactly what we want to do. So obviously these points cannot be the optimal points. Now let's go to point 3. At point 3, del f3 and del c3 become parallel, and what this means is that there is no way to decrease del f3 by not changing the value of c3 as well. And the reason is that since they are parallel, as soon as you move in a direction that is not perpendicular to f3, which is required in order to change it at all, you find yourself going in a direction that is also not perpendicular to del c3. So in theory you could go all the way down to the origin, which was the optima of the original problem, but that would end up violating the constraint. So that's the reason that for constraint optimization, all we need is that the derivative of the gradient should be parallel to the derivative of the constraint. And another way of saying that is that the vector of the gradient of the function should be some constant multiple, which can be positive or negative, of the gradient of the constraint. And another way of writing that is del f minus lambda del c equals 0, which is the same as del of f minus lambda c equals 0. And this is the Lagrange condition. So you can see that we've carried forward the same intuition of unconstrained optimization with only a slight modification, and in this framework we can solve constraint optimization problems as well, which is pretty remarkable when you think about it. Alright, hope you had fun watching this video. Thank you.